on the top of page 4, we start talking about percent yield. And so the first thing that you need to understand is that yield just means something that is produced. So a yield is always talking about a product. So yield means product. So we'll start learning about percent yield with theoretical yield. The theoretical yield of something tells you how much you should be able to make. So theoretical yield is the calculated amount of product that can or should be produced from a given amount of reactant. It tells you right here, you will use the given amount of reactant to determine this. So I'm going to put calculated. This is determined using math, or we're going to determine it mathematically. Using stoichiometry calculations. So you are going to use, as you're given in any of these situations when you're calculating theoretical yield, you are going to use the given amount of reactant to figure out how much of a specific product you are able to make. And then your actual yield is the amount of product that you actually produced when a chemical reaction is carried out in the lab. The percent yield is the ratio of the actual yield to the theoretical yield. This will be expressed as a percentage. So the formula for it, if you want to think of it that way, is actual over theoretical times 100. So if you are the one performing a lab, then the results that you get from your lab, the amount of product that you are able to obtain from your lab, that would be your actual yield. The theoretical yield is by using the amount of reactant that you started with, mathematically calculating how much of that product you should have been able to make. We use recipes as examples for a lot of these things. And so, for example, if I were to make cookies, chocolate chip cookies, and I'm following a recipe I found online, and I get the butter and the sugar and the flour and all of that, and it tells me that I should be able to make 2 dozen cookies. But while I'm making my chocolate chip cookies, I eat some of the cookie dough here and there. Or even if I don't eat some of the cookie dough, but I'm not able to scrape out every single bit of dough because some of it gets stuck in the bowl, or some of it's on the spoon, or maybe some of it's stuck to the baking sheet when I baked the cookies. All of those are ways that you could lose some of your product, resulting in less yield than what you should have been able to make. So in that example, the 2 dozen cookies that I should have been able to make according to the recipe, that would be my theoretical yield based on the ingredients that are going into the recipe. And then however many I actually make would be my actual yield. That's a really good question. The question was, can you ever have more? And the answer is truly no. You cannot ever make more of your actual product or your true product than the amount that the reactant tells you can make. However, there are some examples where you might calculate that you would get more. So, for example, I'm trying to think of a better... Let's say you're making soup. I don't know how much you guys cook, but if you're making soup, and I'm going to draw us like a little pot. Okay, so you've got your pot on the stove, and one of the steps of making your soup is that you need to put broth in here. So I have all this broth, and then you've got all your different little vegetables in here as well. So I've got my greens, I guess some yellow stuff, and I've got little red things. Okay, so you've got all of your ingredients in this soup. And when you make a soup, or maybe a chili is a better way to think of it, because soups you kind of do want brothy. One of the steps of this would be to simmer it and let it reduce. Do you guys cook enough to be familiar with like the term reduce? Okay, so like you do know that? Okay. So if it says reduce, so this is sitting on top of your stove or whatever, and it's heating, and it says reduce. What that translates to is that instead of the liquid level being here, by the time it's done cooking, the liquid level should have gone down, and then what you end up with is like a more concentrated version of your soup or your chili or your stew, right? If you didn't reduce it all the way, if you don't take it down to like the right level of reduction, then you might end up with what seems like more than it was supposed to produce. So if this said it should have made 8 servings, well, let's like be more specific. We'll say like 8 1 cup servings. But when you're done, you actually end up with 10 cups. It is possible to end up with what looks like more than what you should have ended up with, but what that really means is that your final product didn't reduce enough, or you didn't make the correct product, really. So it's like a watered down version of what it should have been. So you didn't actually make more soup, you just didn't make the right soup. Does that make sense? In like a chemistry setting, what sometimes happens, if you remember when we did the separation lab, where part of what you had to do was, that was a terrible funnel. If we had the funnel, and take that, and then you had to put your filter paper in the funnel, right? And you collected your product, and then you took stuff in a beaker. Do you remember this when we had the salt, sand, and iron mixture? You had salt, sand, and iron. You had to use the magnet, get the iron out of the sand, and then you had to dissolve the salt using water, and then you put the whole thing in here, and then what ended up happening was you collected your sand mixture, and then you had salt water, and then you had to take your salt water and then put it onto the hot plate and boil off the water so that you were left with just salt in your beaker. You remember that? So in this one, if you didn't wait for your product to dry, so in that lab we used the drying oven, and we used the hot plate. If you didn't wait for all of the water to evaporate when your beaker was on the hot plate, or if you didn't wait for all of your sand to dry out in the drying oven, and you were left with some water still mixed in with your product, even if it wasn't a lot, but it was just like some water, then it would look like you recovered more than your original mixture, which isn't actually possible. We weren't producing anything new. But if it's wet, that is going to be taken into account in the mass. That was a long answer to your question, but I really like that question, and that's something that I always address here. So it is possible to calculate more than 100% yield. However, it is not possible to actually yield over 100% of the correct product. So let's look at some examples here. It says, in lab, you burned 3.2 grams of magnesium and produced 4.8 grams of magnesium oxide according to the given reaction. So let's start by labeling that. This reaction is what it's talking about below. So I have magnesium reacting with oxygen to form magnesium oxide. And I'm going to start by balancing the equation. So I have O2 on my reactant side. I'm going to need 2 oxygens on my product side. So a coefficient of 2 right here would help me. And then what other coefficient would I need? Perfect. So 2 in front of magnesium, and then it would just be 1 in front of O2 since that's already balanced. So with those coefficients, it tells me I burned 3.2 grams of magnesium. So I'm going to use a different color just so that it stands out a little bit, and I'm going to write above magnesium 3.2 grams. That is one of my reactants, so that doesn't tell me anything on its own about the yield, but I could use that to calculate my theoretical yield. Then I have 4.8 grams of MgO, magnesium oxide, produced. So that would be 4.8 grams right here. Your calculations showed that you should have been able to make 5.3 grams of magnesium oxide. Based on that wording where it says should have been able to make, that is what your theoretical yield is telling you. It's telling you how much can be produced. Another way to say that is should be produced. So I'm going to put in quotes up here, should. So if you should be able to produce a certain amount, that is your theoretical yield. Another thing that points to us knowing that that's theoretical is because it tells me that my calculations showed me that. So if you have a calculated amount, that again tells me it's theoretical. So your theoretical yield in this case is 5.3 grams of magnesium oxide, so I'm going to label that as theoretical. And then, based on the context of the question, what would I label this value? It is grams of MgO, yes. So, since magnesium oxide, yes, correct. Since magnesium oxide is my product, my only product, it's the only thing I'm yielding from this reaction. It says in lab, which matches this. In lab, that would be my actual yield. In lab, what happens is this person takes 3.2 grams of magnesium as a reactant, and that magnesium produces this much. All of that is taking place in lab, which means that this is my actual yield. So I would take my actual of 4.8 grams of magnesium oxide divided by 5.3, because that's my theoretical, so I'm following this equation right here. And then you would multiply that by 100 to turn it into a percentage. So type this into your calculators to figure out 4.8. Oops, 4.8 divided by 5.3, and then multiply by 100. So 90.566 percent yield. Or you could just do 90.57. I like to round to 2 decimal places generally. More is always okay, but I want at least 2 if it's given to you. So 90.566% yield. What this tells us, if we try to add a little bit of context to it, is that we should have been able to produce 5.3 grams. We actually only produced 4.8 grams, or maybe we were only able to recover that much for weighing. So we were able to yield about 90% of what the reaction told us that we could yield. So a lot of times your actual yield is going to be limited by what specific methods you use during lab. So if you think of, I know it was a long time ago, so it's kind of hard to use this example, but the separation lab with the salt and the sand and the iron. If you remember, what we did is we took your beaker, so I'll draw this in a separate little section. We took your beaker, right, and we had a certain amount of salt water in here, so there was salt dissolved in this water. Remember that? And we put it onto the hot plate. I'll draw a fire underneath it. I know we didn't use flames, but just to remind you that it's hot. Okay, so hot plate, heating up this, which reduced the water level to get rid of all of the water. And then your goal was to recover that salt, right? Remember enough? If you left this uncovered, then what happens as your water level gets lower and lower and lower and lower is then sometimes your salt crystals start to pop out. It's almost like popcorn, they start leaving your beaker. And then you're left with little splatters of dried salt out on your lab bench. They escape the beaker. And so that when you go and take the mass of your final product, you lost some product in the process. So you weren't able to actually recover all of the salt that you started with. So your yield was less than what it should have been because some of it was lost in the process. You following that? Or if you use the same cookie dough example as before, when I make cookies, like, I will scrape the bowl with every single thing and, like, make sure that none gets wasted. Same thing with, like, brownies. Anything that's got, like, a good tasting batter, I will make sure, like, every last little bit is taken up. Now, I don't know if all of it makes it into the cookies. Like, sometimes I just, like, eat it off the spoon or whatever. But some people aren't as, like, I don't know, if you watch cooking shows, a lot of chefs, like, they're just, like, working so fast, they don't take all this time to, like, scrape it all the way out. They just go quickly. And so some of their product is lost because it just sits in the bowl and they don't actually turn it into whatever it's supposed to make. So based on the process that you're using, things are naturally lost in that way. So let's look at another example. So this example 2 says, use the picture to the right. After performing the following setup, you collected 157 grams of calcium carbonate. What is the percent yield of calcium carbonate for this experimental setup? So if I'm looking at this, I have calcium, calcium carbonate, and zinc. This is the same picture that's on your homework assignment, except there I think you're looking for an amount of zinc, so that's why there's a question mark there, but that's not really relevant for this question. So using the picture, you collected 157 grams of CaCO3. It doesn't say in lab, but it does say after performing the following setup, which implies that there is an action there. So this is telling me that something happened that you were doing this. So I would take this as my actual information. So if you collect 157 grams of CaCO3, that 157 grams would go right here, and the number that it's showing is kind of grainy, but 152 grams is what, according to the law of conservation of mass, says should have been made. So this should be what I produced, but I actually got 157. So again, your reaction, or sorry, your equation is actual over theoretical times 100. So then you'll do that. Your actual was 157, since that is what you got when you were performing in the lab. So 157 divided by your theoretical yield. So it says you should have been able to produce, try to erase that. Maybe not. Should have been able to produce 152 grams. And then you need to multiply that by 100. So just looking at this, since your numerator is larger than your denominator, you can predict that your value will end up being over 100%. So when you divide this goes right along with Giovanni's question from a minute ago. So 157 divided by 152 gives me this number. This is why I recommend, even if you're pretty good with decimals, a lot of students get confused when this is the answer that they calculate. So type into your calculator times 100 if you don't remember how to convert that into a percentage. So this would be 103.29% yield. So what that number would tell me is that I calculated that somehow I ended up producing more than 100% of what should have been able to be produced. Now, we don't have a ton of context for this, but just based on the pictures alone, you can tell that something is in an aqueous solution. So it even tells you aqueous solution, aqueous solution. And if you are measuring your product, remember, aqueous solution means that it's dissolved in water. So this could be another one of those examples where maybe when you're measuring your product, you didn't dry it out all the way, and so you measured that you actually produced more than what you really did produce. So then example 3 says during a lab experiment. So during a lab, your ears should already be thinking of what type of yield, actual or theoretical, if it's happening in lab.
Actual.
Your actual. Good. Okay, so during the lab, 24.8 grams of calcium carbonate, not just calcium. So grams of calcium carbonate. My button on this pen is given out. So 24.8 grams is decomposed and 13.1 grams of calcium oxide is produced. This information, both of them, this and this, that gives me actual information. The difference being that this is a reactant, so that would not be an actual yield because that's a reactant, and yield is only talking about products. This 13.1 grams is talking about a product, so this would be an actual yield. So to determine an actual yield, I'm looking at products only. The equation needs to be balanced, and this one just happens to already be balanced. I have 1 calcium, 1 calcium, 1 carbon, 1 carbon, and 1, 2, 3 oxygens, and 1, 2, 3 oxygens. So since we're balanced, our coefficients would all be what? 1s. Perfect. Okay, so the actual yield of CaO is what we already identified right here, so that's just 13.1 grams. I can tell that that's my actual yield because the question says during a lab experiment. I actually started with 24.8 grams of CaCO3, and when that reacted, it produced this much CaO. So then it says, what is the theoretical yield? This is my calculated yield. And so in this case, since it didn't give me any kind of calculation, so up here it said, according to your calculations, the theoretical yield was not provided to us. That's where you need to use the given amount of reactant like we outlined in the definition. So remember, the theoretical yield is the calculated amount of products that can be produced or should be produced from a given amount. Kind of glitching. What is happening? Let's see if I can. From a given amount of reactant. Sorry about that. So scrolling back down to the question that we were on, I need to take the given amount of my reactant, the 24.8 grams, and turn that into grams of calcium oxide. So theoretical yield, I'm going to put a note here. Something is happening with my tablet that's not cooperating. I don't know. It was working okay a second ago. Yeah, I think I might cut this one off. I'll give it a second to think, and then we'll see if Alright, I'm going to pause this real quick. Alright, I guess we'll see what happened with that. If it wasn't recording, then we'll get rid of this one. But I think it should work now. So the question was, what is the theoretical yield of CaO? And so I had just gotten done saying we're going to use the given amount of our reactant. So 24.8 grams. I keep circling calcium. It's calcium carbonate of CaCO3. So I'm going to take 24.8 grams of CaCO3, and then I need to turn that into grams of calcium oxide so that I can compare it to the 13.1 grams of calcium oxide from right here. So I'm going to bring grams of CaCO3 down to the bottom and put moles of CaCO3 at the top. I'll bring moles of CaCO3 to the bottom, and from moles of CaCO3 I can go to moles of anything else in my equation. So in this case, since I'm interested in information on calcium oxide, I'm going to go to moles of calcium oxide. I'll bring down the units of moles of calcium oxide, and then I can go to grams of calcium oxide. So right here I have grams to moles, which is molar mass, and then here I also have grams to moles, which is molar mass of a different substance. So for each of those, you're going to have 1 mole that is equivalent to the number of grams that you would calculate from your periodic tables. And then for this, in the middle, I have moles of calcium oxide to moles of calcium carbonate. That is a mole ratio that comes from the coefficients in my balanced chemical equation. And since this equation is already balanced, my coefficients are all just 1s. So I get 1 to 1 right there. So I'm going to go back to the periodic table for you all to be able to calculate 2 molar masses. So you need the molar mass of CaCO3, and you need the molar mass of CaO. So calculate each of these, and the number that you calculate for this one will end up going right here, and the molar mass that you calculate for this one will end up going right here. So I'm going to pause right there, let you calculate this real quick. Remembering that you don't round your periodic table, the molar mass that you should have calculated for calcium carbonate is 100.088. That's what y'all said, right? Okay, and then for calcium oxide, what molar mass did you calculate? 56 point what? I agree. Perfect. All right, so then when you type this into your calculator, you do 24.8 times 1 times 1 times 56.079 divided by 100.088 divided by 1 divided by 1. So multiply by everything on top, divide by everything on bottom. But of course, you don't have to actually type in the ones because first of all, they would cancel out. But second of all, they're not going to change your answers even if they don't cancel out. Dividing or multiplying by a 1 will give you the same value no matter what. And your final answer then would be 13.895, correct? So 13.895, you can round your final answer when that's what you're submitting. So I would maybe round this to 13.90 grams of calcium oxide. And this number is my theoretical yield of calcium oxide. So I used my given information on the reactant and then plugged in my molar masses for everything to calculate the grams of calcium oxide. And now for percent yield, I still need to take my actual divided by my theoretical, and then I multiply by 100. And so I would take my actual yield of calcium oxide, so 13.1 grams, divided by my theoretical yield of 13.9 grams. And then I multiply that by 100. So 13.1 divided by 13.9. And then yes, definitely. Yep. So if you didn't want to round it when you got your 13.90, that's okay. You can always keep more decimal places. It's just that when you round, I want you to keep at least 2. So then your final answer here should be what? 94.24. If you didn't round when you divided, did it change your final answer at all? Okie doke. As long as what you are showing me on your paper matches as far as rounding. So if you rounded to 13.90 and this is what you plug in here and then you get that number, that works. But if you didn't round it and you kept this whole thing, then this is the number that you should have been showing down there. But either way, close enough and that works. All right, last example on this page says during a lab, 1.87 grams of aluminum reacts with an excess of copper 2 sulfate. Was excess part of this one at all? No. So this phrasing right here, reacts with an excess of something, what that is telling you is that copper 2 sulfate, first of all, is my excess reactant, and second of all, will not run out throughout my entire reaction and therefore will not be used towards any calculations of what was produced. So I'm going to label all of this. I have 1.87 grams of aluminum. I have an excess of copper 2 sulfate. So what that means is I basically have an unlimited amount. So I'm drawing a little infinity sign above copper 2 sulfate. That means I have as much copper 2 sulfate as I could possibly need. And then 4.65 grams of copper will be produced. So I have 4.65 grams of copper produced. This is asking what is the percent yield. So based on the way that the question is worded, I have an actual yield given to me, and then I need to use the amount of reactant that I started with, the amount of reactant being this much aluminum, since I won't use infinity in my calculations, and then turn this into grams of copper. So I need to calculate the number of grams of copper able to be produced from 1.87 grams of aluminum. And then that will give you your theoretical yield. Of copper. So then after you get theoretical, then you would take your actual yield and divide it by your theoretical, multiply by 100, and that is how you would find percent yield of copper in this question. So I'm going to pause here, walk around and help you all calculate this. You should set up your T-chart using this information.